In the previous section, we saw a process for calculating the area under a curve on an interval from A to B. And I want to review that process and actually see how we can extend the idea of that to include this process for more functions than just positive functions. So calculating the area under the curve, we assumed that the function is always positive on that interval. So in this case, f of x is positive for all x in the interval from A to B. So in this process, we start by picking an n. And so it's a positive integer n. And we divide the interval up into n subintervals of equal length. And we're going to name the length of each subinterval. So we're going to call that delta x. And that is the difference between b and a divided by n. So the interval from A to B has length b minus a, and we've divided it into n equal pieces. So each piece is going to have width b minus a over n. We're calling that delta x. And the next thing we will do is we're going to pick a sample point inside each subinterval. So before I do that, I just need to pull in some notation and say that we're going to label those subintervals. So let me just draw this. I'm assuming that I have like lots and lots of these subintervals, and I'm going to put some dot dot dots to indicate that I'm not showing all of them. Okay, so there's a bunch of subintervals, whatever n is. And I'm going to label the border points of these subintervals as x sub 1, x sub 2, all the way up. And so basically like the right end of the subinterval is going to be indexed with the number of what interval it is. Okay, so the first interval has x1 as its right endpoint. The second interval, the second subinterval has x2 as its right endpoint. And so we go all the way up to the nth subinterval has xn as its right endpoint, and that has to be b. And so we will call a equal to x sub 0. Okay, so there are n subintervals. That means there's n plus 1 border points. So let me write that. The border points of the subintervals are x0, x1, dot, dot, dot. I'm going to leave a couple in the middle. xn minus 1 is the second to last one, and x sub n is the last one. And it's worth pointing out that x0 is a and xn is b. And in the middle, we're going to call the middle, like generic subinterval is going to go from xi minus 1 to xi. Okay, this here is going to be the ith subinterval. Okay, if you haven't figured this out already, this is a very notation-intensive section. Okay, so in each subinterval, we are going to pick a sample point. And so I'm going to say in the ith subinterval, which is the generic subinterval, we're going to pick a sample point called xi star. Okay, that star just basically means it's not designated, it's whatever we choose. So in the previous section we had if we wanted left Riemann sums, if we wanted left approximations, then we would choose all of our sample points to be the left endpoint of each interval. or we might choose all of the sample points to be the right endpoint of each interval. And it turns out that it doesn't matter whether we choose left or right, or middle, or some random number inside the interval. I will show you an example of that in a little bit. Okay, I got distracted with notation. Let me just go back and say what we're doing. We're taking that interval from A to B, we're dividing it into n equal subintervals, okay? And in each little subinterval, we're gonna pick some sample point xi star. And then we're going to build a rectangle on the ith subinterval, on each subinterval, where its height is going to be determined by the value of the function at those sample points. Okay, so suppose I pick some point, I don't know, I'm gonna just because it's hard to draw in this tiny little space, I'm gonna pick some point kind of close to the middle, and then I am going to say that the height of that rectangle should be f of xi star, which is right there, and I'm going to build a rectangle on that subinterval. So I will build a skinny little rectangle with width delta x and height f of xi star. Okay. Now we have an approximation of the total area, which is the sum of all of those areas of little rectangles. So it would be f of x1 star times delta x plus f of x2 star times delta x plus dot 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 f of xi star times delta x plus dot 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 plus f of x sub n star times delta x. Okay, each of those is height times width of a skinny little rectangle. Okay, and that is, we write now in shorthand with that summation notation, the sum of terms that look like f of xi star times delta x, where I runs from 1 to n. Okay, this is an approximation, and of course we have larger values of n give us less error, so that gives us better approximations. Picking a larger value of n means starting over, building a new set of subintervals, choosing new sample points in each subinterval, and getting a whole new sum. Okay, so if we repeat this process with a larger value of n, that gives a better approximation of the area. And then we say that the area is actually equal to the limit of this whole process as n goes to infinity. And it's going to be like this. Sum as I equals 1 to n of f of xi star times delta x, provided the limit exists. We always have to put that caveat whenever we define something to be a limit. Okay, so this is the whole process, and I wanted to go through this process again, partly because there are going to be many, many situations where you are going to see this process repeated for different situations. Okay, so it's kind of worth looking at this process several times because it's just going to come up over and over. You know, there's going to be a lot of things in this world that you're like, oh, well, how do I calculate the volume of this thing? And the way that you calculate that volume of this thing is you slice it up into slices and calculate the volume or approximate the volume of each slice, and then, take a limit as your number of slices goes to infinity. Okay, so this is a very, very common process. So it is worth getting accustomed to this whole setup. But so I want to just take a moment to review what we did. We're looking for calculating the area under this curve. It's this kind of wonky, curvy area that we don't have a reference for from our geometry. And so what we do is we slice the area up into a bunch of slices, and then we approximate each slice with an area of a rectangle. Okay. If we actually were to make those slices on the n subintervals, each of those pieces would not quite be a rectangle. It would be like, the top end is a little bit curved, but we approximate with a rectangle. And then we add up all of these rectangular approximations to get an approximate value of the area. And then we get a better approximation with larger n. And so our area becomes the limit as n goes to infinity of doing this process. This is a process that we do that has a meaning of calculating the area under a curve for a positive value function, okay? And the thing is, there is nothing that stops us from doing this process to a function that is not everywhere positive. And so then the question becomes could we do this with any function? And the answer is yes. If you look at what we've done here, we just took an interval from a to b on which f is defined, and we divided up that interval into n equal pieces. We took a sample point in each piece, and then we took the value of the function at each sample point and multiplied it by this delta x. Okay, that delta x is something that's just about b minus a over n. And we just took the value of the function at a sample point. And so we could do exactly the same process with any function, whether it's positive on that interval or not. And the thing that we would get is basically if ever the function were negative for some portion on the interval, then we would just be multiplying our delta x by a negative value. And so all of the pieces that kind of hung down below the x-axis would have a negative value on them. So I want to take a look now on Desmos just to kind of see what this looks like. Okay, so here is the curve y equals x squared, and we're just looking on the interval from 0 to 1. And right now I'm looking at the sample point is on the right endpoint of each interval. So I'm taking the height of each rectangle is the value of the function at the right endpoint of the rectangle. Okay, I could also choose to use the left endpoint. I could choose to use the midpoint of each, let's see, 0.5, there it is. I could choose to use the midpoint of each interval. I could also choose to have some randomized point in each subinterval. And, there's some error here, but if I take my, take more and more subintervals to do this approximation on, I lose that error. Okay, so this is just with n equals 100. And we've already calculated this particular integral to be 1/3. So we could see that that's getting pretty close there. Okay, and so actually using the midpoints is actually a really good approximation for this particular curve. So I want to show what it looks like if I'm going to bring this down to some manageable number and look at what happens if we have some negative values in the function. Okay, and so what this does, we still have this sum of f of the midpoint times the width of the interval. In this case, the width of the interval is 1/8 because we have 8 subintervals between 0 and 1. And so the width of each subinterval is 1/8. And then instead of calling it the height, it's just the value of the function. So here the value of this function is negative, so I'm multiplying a negative number times 1/8. Here I have another negative number times 1/8, 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 and then we have 2 positive numbers times 1/8. Okay, and so the end result when I actually take the limit of this as n goes to infinity is basically this process that I have gives me a net signed area. Okay. Net means, the balance of all of the positives and negatives. And so all of the stuff that's above the x-axis, that's in this case colored blue, is going to have a positive sign associated with it. And then all of the stuff that hangs below the x-axis, in this case, that is colored orange in this case, is going to have a negative sign associated with it. So it's basically all of the positive areas, or all of the areas of the stuff above the x-axis minus all of the areas of the stuff below the x-axis. So that's the net signed area. And I want to go back to this definition and just kind of say we can do this process for any function, whether it's positive or negative. Let me write that. Okay, and then the resulting value from that we get from this, if the limit exists, is the net signed area between the function y equals f of x, between the graph y equals f of x, and the x-axis. And we call this the integral of f on the interval from a to b. Okay, and so the symbol that we use is we write something that looks like a long, elongated, smooth little s for sum, and we write a little a to b for the bounds of integration or the limits of integration. And we write f of x dx. For now, we just kind of think of that dx as being just part of the notation, saying that x is the independent variable that we are integrating upon. And so this is defined to be the limit as n goes to infinity of the sum I equals 1 to n of f of xi star times delta x, where all of that stuff that is in that sum is basically taken from that big process named above. Okay, it's just for every n, you divide the interval from a to b into n subintervals. Each subinterval has width delta x, which is b minus a over n. The xi stars are sample points in each of the subintervals. Alrighty. A little note, I keep saying provided the limit exists. And so I will note that these limits will exist anytime that we have that f is a continuous or piecewise continuous function. So in more advanced topics in Calc 2, you might see that the limit might not exist. You have to be more careful if, for example, f is continuous on the open interval from a to b, but not necessarily continuous all the way up to those endpoints. Or if there's, checking if there happens to be like an asymptote, a vertical asymptote in the middle of that interval. We're not going to worry about that for now. We're just going to say, for now, all of the functions that we're going to be dealing with, that limit is going to exist. So we're not going to worry about that too much. Okay, so here now this is the introduction of the definite integral.